Hello, everyone. Thank you for coming to session 6 on simulating quantum systems. John Morton's going to start us off on engineering and exploiting spin dynamics of donors in silicon.
Great, thanks very much. You'll see I've dropped the exploiting from the title. I don't want to corrupt this talk with any discussion of applications. So it's really just going to be about engineering spin dynamics, specifically spin relaxation using donors in silicon. Again, in one sense, donors in silicon have been studied for a very long time. The very first pulsed electron spin resonance measurements were done using phosphorus donors in silicon. But recently, there's been a revival of interest in them, motivated by applications in quantum computing using the spins of donors in silicon as quantum bits. Initially, the interest focused on phosphorus donors in silicon, probably the most abundant donor as used in conventional information processing. But what I'm going to be talking about is really moving down group 5, there's a terrible pun coming, to bismuth, where there are interesting spin properties that we can use to demonstrate different ways to control relaxation. So the subtitle is Donors in Silicon Get Down to Bismuth. Many people contributed to this work. I'm going to talk a bit about clock transitions. That was the work of Gary Wolfowitz, now in the Acknowledgements group in Chicago. And also at the end, I'm going to talk about the Purcell effect and cavity-enhanced relaxation spins. And these experiments were performed by Audrey Biant-Affaire and Jared Pla, and the experiments were carried out within the Berthet's lab in Saclay. Okay, so this talk is going to be about spins. So let's start by looking at the state of a spin within a magnetic field. We have these eigenstates, spin up and spin down, and this spin, this first spin 1/2, can exist in some superposition of those states, and we can use various ways to express this, but we can use a theta and a phi to describe the state. Theta then tells us the relative population of these eigenstates, how much is spin up, how much is spin down, and phi describes then the phase or the coherence of this spin. So then there are two ways that this state can get corrupted, and we use two timescales to define them because they can often be very different. We talk about T1 or spin relaxation, which is basically theta going wrong. It's changing the relative populations of spin up and spin down, and that typically it involves energy exchange between the spin and the environment. And the second time scale we call T2 is decoherence, or in other words, the loss of information of phi, or a dephasing of the spin. And because that doesn't necessarily involve energy exchange with the environment, that often occurs on faster time scales. And we're interested in both of these timescales to some extent. If you're really interested in making spin qubits, T2 is critical because that's the timescale on which a quantum bit turns into a classical bit. But T1 is also important. That also tells us, if we just use thermal processes, how long it takes to relax, for a spin to relax to thermal equilibrium. So in this talk, I'm going to begin by giving an introduction to donors in silicon, a system we haven't heard too much about today, and then talk about the use of clock transitions and quantum baths. And that's really about engineering T2 in a system. And then finally, I'm going to talk about the Purcell effect for spins, which is about engineering T1. So this is really taking the same system and looking at what kind of tricks can I play with a Hamiltonian or with an external body like a cavity to control these relaxations in a single, these relaxation processes in a single system. Okay, so first of all, I'll begin by talking about phosphorus, this most commonly studied and perhaps simplest donor in silicon. It's substitutional, so we take a lattice of silicon, we replace one of these atoms with phosphorus. Phosphorus has a nuclear spin of 1/2, which is useful, and this is what the conventional semiconductor industry does, and they do it so that this extra electron can exist in the conduction band. We cool the system down so that this this electron becomes bound to the donor. So now we have these two spins, the electron spin half coupled to the nuclear spin half. This is the spin Hamiltonian. We have the Zeeman term for the electron spin, the Zeeman term for the nuclear spin, and then finally there's an isotropic hyperfine coupling between the electron and the nuclear spin. So this is the level structure that you end up with. You can see the electron spin here shown in blue and the nuclear spin in red. And all of these transitions are now very well resolved. So we can drive this transition using what's typically microwave pulses, and that's distinct from this transition thanks to the hyperfine coupling. And you can also use NMR to drive these. So really you can think about this in much as you would an atomic system, just happens to be sitting within a piece of semiconductor. Here's an example of the electron spin resonance spectrum of phosphorus. This is under a constant microwave frequency, looking at absorption as the magnetic field is swept. And so you can see the two different resonances corresponding to these two different microwave transitions. You can see they're very well resolved. Okay, so I said this was really a talk about relaxation and decoherence. So I'll say a bit about how we measure decoherence in this kind of material. The experimental setup crudely looks like this. We have some kind of sample. This is phosphorus doped silicon in this case, and it sits within a microwave cavity. We have to apply a magnetic field, and as I mentioned, we need to be at low temperature. And so we have a microwave source, and that provides microwave pulses that can excite the spin. This causes rotations of the spin around axes defined by the phase of the microwave pulses. And then when these spins are coherent, they will emit a weak microwave signal that gets picked up by some detection arm, which is referenced against the microwave source. Now, because of inhomogeneous broadening, when you excite spins, this is the animation you're looking at here, when you excite spins from their eigenstate into the plane, you'll see that the different spin packets evolve in different directions in the rotating frame. And so you have a form of decoherence, but it's reversible. It's coming from the fact that every spin is experiencing a different magnetic field. And so by applying a second pi rotation, we can effectively invert the effect of that inhomogeneous broadening and bring all the spins back together in phase to produce what's known as a spin echo. So typically, when we talk about decoherence, we talk about the irrecoverable part of the phase information, not due to inhomogeneous broadening, but due to other dynamical effects within the environment. And so we'll typically look at this echo intensity as a function of this duration t for which the spins are in this coherent superposition. So here an example of some decay curves showing this echo intensity as a function of this delay, showing decoherence of this ensemble of phosphorus donor spins in silicon. So first of all, you can notice the time scale. It's in the sort of hundreds of microseconds. But also, these different angles marked here represent the orientation of the silicon crystal with respect to the applied magnetic field. So it's telling us that there's some, although on the surface this donor is isotropic, it's got a spherical wave function, isotropic hyperfine coupling, there's something to do with the lattice crystal structure that's affecting decoherence. And to answer that, we then need to consider the isotopic composition of silicon. I've shown here a cartoon of the donor wave function, and I've just dropped in a few silicon unit cells. And 5% of natural silicon is silicon-29, and that has a nuclear spin of 1/2. All of the other isotopes of silicon is spin 0, and these are the lemons in our picture. They're what's causing decoherence. So if we, I've dropped a few of these down in the sort of region of the donor wave function, and what we need is some dynamics to drive decoherence, and that's going to be given by the dipole coupling between these nuclear spins. Now that goes as 1/r cubed, So actually, nuclear spins that are more than one lattice site apart interact too weakly to drive decoherence. We only need to consider nuclear spins that are nearest neighbors because of this 1/r³ effect. And now you can begin to see why there's this orientation dependence. It's because of the angular dependence of the dipole coupling. But still, the pictures are a bit more subtle because the nuclear spins are coupled to the electron, and in order to evolve, so if you have two nuclear spins that are dipole coupled, if they both spin up, nothing happens. If they both spin down, nothing happens. But if one is spin up and one is spin down, then they can evolve and flip-flop, and it's that dynamics that can drive decoherence. But in order to be able to do that, in order to be able to flip-flop, they need to have the same energy. And the ones that are too close to the center of the donor wave function, their coupling to the donor electron is varying too quickly, and so they're too different in frequency. That's illustrated here in the color. So these two nuclear spins, they're too different. Their transition frequencies are too different due to the strong coupling to the electron, and so their dynamics is frozen out. And so, although they're strongly coupled to the donor, they don't drive decoherence. Similarly, you can imagine what happens for nuclear spins that are far away. They're perfectly on resonance. They will flip-flop very effectively, but the electron spin doesn't really care. So this is a kind of dilute, watered-down form of lemonade. And you can imagine that there's some intermediate region where you have spin decoherence operating most effectively, where nuclear spins are reasonably well coupled to the donor. So there's this band of spins in the vicinity of the donor, and their flip-flopping dynamics is driving decoherence. Okay, so we can solve this problem by getting rid of the silicon-29. This is actually was achieved for purposes completely unrelated to qubits or decoherence. It was all about defining the kilogram. There was a project called the Avogadro project, which aimed to develop a sphere of silicon-28 that was very round. It had a very high degree of precision in terms of the number of atoms within that, thanks to the lattice constant in silicon and its purity. And they would use that to redefine the kilogram instead of using a metal rod sitting in a vault in Paris. So this was the crystal that they grew of silicon-28 with less than 100 ppm of silicon-29, and of course all the other impurities, elemental impurities at much lower levels. And when they were cutting this into spheres, we were fortunate enough that some of those pieces wound their way into the community that was interested in spin decoherence. And if you study the decoherence times of phosphorus donors in such material, you can see it goes out to much longer times. Now electron spin decoherence times go out to about 20 milliseconds. And incidentally, just so you have the reference, T1, the spin relaxation time, goes out to minutes or even hours at very low temperatures. So that already looks like quite a respectable coherence lifetime, especially for a solid state system. But we can ask the question: can we go even further? So with that introduction out of the way, we'll move on to bismuth. Now, bismuth, as I mentioned, has a number of interesting properties. They come from the nuclear spin of bismuth-209, which is 9 halves. And that gives you a much richer level structure now, this 20-dimensional Hilbert space. And also another important feature is this very strong hyperfine coupling. Bismuth is a deeper donor, so it draws in the electron wave function more compactly, and so it has a greater overlap with the bismuth nucleus. So at high field, we can label these states according to MS and MI. But at low magnetic fields, we need to think about the total angular momentum, and we use F and MF as the quantum numbers to describe this region. So if we then take this level diagram and plot what are the allowed transitions within this system that we can drive that couple to microwaves, we see that they look like this as a function of magnetic field. And there are 4 interesting points on this plot. And to help, I've circled them in blue, and these are what we call clock transitions. They have various other names. And the key point is that there's no first order dependence of this transition frequency on the magnetic field. And what that means is that anything that looks like magnetic field noise or magnetic field inhomogeneity doesn't, to first order, lead to a change in frequency and therefore the energy and therefore the phase of the spin. So these are points at which we can expect the spin to be robust to magnetic field noise. Just to illustrate that graphically, with this relation, we can plot this first derivative of the frequency with respect to field. You can see these points going to where df on dB goes to 0. What that means is that if there's some static variation in magnetic field, due to magnetic field inhomogeneity, that's going to have less of an effect on the line width and energy, and similarly, noise is going to couple. Magnetic field noise is going to couple less strongly to the spins. So we wanted to study these points. They occur at very particular values of frequency and magnetic field. So we built a loop gap resonator to perform ESR around 7 gigahertz. And this then shows how you tune the resonator to exactly match one of these clock transitions. So if you imagine doing a magnetic field sweep at a certain frequency above, near but above this clock transition, you should see these two resonances. That's what you see up here. If you do this frequency sweep as a function of magnetic field, you see. Let's focus on these two peaks shown in dark blue. And then as you reduce the frequency, the two peaks come together, broaden out, and at the point just before it disappears, say here, you know you're at this clock transition where to first order the magnetic field dependence is going to 0. So then this is a measure of the spin decoherence time for bismuth donors at this clock transition in natural silicon with all of these silicon 29 spins. And you can see that the decoherence time has now gone, so for reference, away from the clock transition, T2 is about 500 microseconds. It's gone all the way up to 100 milliseconds. So despite the presence of these silicon 29 spins, it looks like an effective magnetic field to the bismuth donors, and so their effect is strongly suppressed. We can also, I guess, look at the effects, the changing nature of the silicon 29 bath around these points. And one way to get an insight into how to understand this bath, is it is a classical bath, is it a quantum bath, is to use a dynamical decoupling. The dynamical decoupling, actually I've already shown you one form of it. This Hahn-Echo sequence is a type of dynamical decoupling where you're suppressing various kinds of noise in the environment. The Hahn-Echo is good for suppressing static noise, and it works because the magnetic field experienced by the spin in this period of its evolution is the same as in the subsequent period, and so any phase which spins pick up over here, when it gets flipped, that phase is inverted, and that's why all the spins come back together to form the echo. That assumes that that this magnetic environment of the spins is constant. If it varies, of course, then they don't all come. The phase that's picked up here is not all unwound, and so they don't all form an echo. But you can get around this by flipping the spins periodically with a high frequency, and that then it suppresses decoherence because it means that now the spins are only the sequence are only sensitive to changes in the magnetic field between these shorter time periods. So just to put it in a different way, perhaps you can think about dynamical decoupling for a classical noise source simply as a filter function. Whereas you apply more and more pulses, the filter gets narrower and narrower, and the central frequency of this filter is simply a function of this period tau. So that's for a classical bath. If these nuclear spins are simply producing some kind of Gaussian noise, then I can understand the effect of dynamical decoupling simply by applying a filter function to this Gaussian noise. If, on the other hand, I argue that the nuclear spins are not a Gaussian noise, that they're quantum spins, they couple to the donor in such a way that there's back action, between the donor state and the nuclear spin bath, and maybe I should instead be thinking about the nuclear spins being entangled with the donor spin, and so I have this donor bath entanglement. That obviously could not be described in a simple Gaussian model using filter functions. So what we can do is we can look at experiments on decoherence under dynamical decoupling. Those are the points. And then we can compare this with a quantum model where we simulate these clusters and we look at entanglement between the donor and the bath. And we compare this with a semi-classical model where we purely model the nuclear spin bath as Gaussian noise. So if you look at this high field limit far from a clock transition, if you compare the dashed lines and the dot and the solid lines, you can see that there's a large discrepancy between the semi-classical and the quantum model, and only the quantum model is able to reproduce the experimental decay curves. So what that's saying is that normally, far from a clock transition, we have to think about this silicon-29 as a quantum bath, that we have entanglement between the donor and the bath of nuclear spins around it. But as we move closer to this clock transition, well, the donor spin is becoming less sensitive to the bath, and of course the bath is therefore feeling less of a back action from the donor spin. And so now you can see that the classical and the quantum model overlap and fit well with the data. So in that regime, because of the reduced interaction between the donor spin and the silicon-29s, we can treat the silicon-29 as a classical Gaussian bath. Finally, we can of course do what we did earlier and remove the silicon-29s. So they're gone. We're now left with residual decoherence mechanisms coming from the coupling between different donor spins, but that coupling is also suppressed as you go towards this clock transition. So you reduce the F on dB, and out here you can see the limit at a clock transition of the longest coherence times that we've been able to measure so far. So at the lowest doping concentration, we measure a T2 of 3 seconds, where the comparable T2 far from a clock transition is 30 milliseconds. And this is currently a world record for electron spins in the solid state. Obviously, there's an inverse there because we're interested in longer times, not shorter times. Okay, so that gives you an illustration of how spin decoherence can be engineered in the same system by taking the Hamiltonian, the spin Hamiltonian, and looking at its behavior in different points, different magnetic fields and frequencies. Now I'd like to move on to talk about engineering T1, spin relaxation. Now, at the beginning of yesterday's talks, there was already some discussion of a cavity QED, and this very much builds upon those ideas. That were very much pioneered in atomic physics, and is something that is since being developed in solid-state devices. So we have some two-level system. We'll put it in a cavity, and there's some coupling between the two-level system and the cavity G. There's some leakage rate from the cavity kappa, and there's some leakage or decoherence from the spins gamma. So there's various regimes of what we can call strong coupling between the atom and the cavity in this kind of picture. Either we have G, which is much larger than kappa and gamma, which means that any excitation simply oscillates back and forth between the atom and the cavity. That's an interesting regime for certain applications. But another interesting regime in the limit of high cooperativity, where the emission rate from this cavity is much larger than gamma, allows us to take an excited spin state and deterministically emit a photon from the cavity, which is related to the phase of the state. So those are two types of strong coupling in this system. And as I mentioned already now for many years, that these kinds of ideas have been applied in the microwave domain in the solid state using superconducting cavities and the two-level system provided by this superconducting qubit as an artificial atom. Now, we can also ask the question, well, can this be applied to spins? In other words, have ensembles or single spins that are coupled to these superconducting cavities. But it's, there are various challenges here. First of all, you tend to apply magnetic fields, and they don't, superconducting films don't necessarily like magnetic fields. The coupling between spins and the cavity is always very weak compared with electric dipoles. You have problems with inhomogeneous broadening, finite spin coherence times. But despite all those challenges, if you can do this, there are opportunities in making multimode quantum memories using spin ensembles, or even long-range coupling of individual spins. So the work on coupling spins to cavities, sort of strong coupling limit, has been going on for several years. There's work on using NV centers in Diamond, both at Saclay and in Yale by Dave Schuster. And then more recently, there was an exchange of a quantum state from a superconducting qubit via a superconducting resonator into an ensemble of NV centers and then back into the qubit. And so you can see here oscillations in the state, showing the state bouncing back and forth between the qubit and the spin ensemble. But you can see that the decay rate is extremely fast, and the fidelity of the transfer is poor. So one way to, of course, to solve some of these challenges is to use bismuth. It offers very long coherence times, as I mentioned in the first part of the talk, but also because of this level structure, you can see that even at zero magnetic field, there are transitions in the regime of 7 gigahertz. And so we don't need to apply very large magnetic fields, and we can still address this system using reasonable microwave excitations. So then the goal is to use cavity-enhanced spontaneous emission of microphotons to engineer spin relaxation of this system. Okay, so again, some very basic atomic physics. This is spontaneous emission of a two-level system expressed as a function of the gyromagnetic ratio and the frequency of this transition, and that governs the rate at which this two-level system will simply spontaneously decay into its ground state. To give you some numbers for a proton in a typical NMR field, the spontaneous emission rate is about 1,000 times the age of the universe so far. Whereas, on the other hand, for an electron spin and a typical ESR frequency, the spontaneous emission time is 10,000 years. So, to actually quote an ESR textbook, which sort of understated it in my view, this is not significant on the usual time scale of longitudinal ESR. So, we don't typically have to worry about spontaneous emission. On the other hand, if you look at optical transitions, it's very common to have spontaneous emission rates much less than a second, and so it's a common phenomenon in that regime, but not for spins. So then we can go back to 1946, to the APS March meeting, right after the first one, after the end of the Second World War, and there's a nice abstract here from Purcell, where he points out that the spontaneous emission rate can be enhanced by putting this two-level system into a cavity. It's enhanced by this, what we call the Purcell factor, which is related to the Q factor of the cavity, its the wavelength and the volume of the cavity. So if we can make a high Q, small cavity, we can strongly enhance spontaneous emission. Actually, he proposed it for nuclear spins. That was the original idea. And so if we take this enhancement factor multiplied by the spontaneous emission rate and tidy that up, we can see this new rate of spontaneous emission in a cavity goes as Q over V, the Q factor, divided by the volume of the cavity. And we can also express that as 4G squared over kappa in the previous language. So to give some numbers there, if we use a typical commercial ESR cavity with the Q and the mode volume that it has, we can get the Purcell spontaneous emission time down to 90 days by shrinking the cavities down using these gold micro resonators. That falls down to about an hour, And then if you can use a superconductor to get a really Qs of 100,000 and keep the mode volume small, you might hope to get this cavity-enhanced relaxation time all the way down to a second, which should be compare well with that of donors in silicon. The resonator here is a typical LC resonator that's made of patterned aluminium on top of silicon. And this is patterned on top of a piece of silicon which has been doped with bismuth. So the bismuth atom, bismuth donors reside underneath the resonator. There's a picture. These are two resonators that were made with Qs of 100 or 300,000. And these are their frequencies, so that you can see that you might hope, as a function of magnetic field, to hit these resonances shown. And indeed, this is what the echo-detected magnetic field sweeps look like. You can see each of these transitions. The line shape looks a bit awkward, but for reasons I can explain later. But each of these is associated with those transitions in the bismuth. And so by sitting on one of those peaks, one can then measure the T1, this relaxation time of the electron, by first flipping the spins, waiting, and then measuring using a spin echo. And so here's a decay curve using the resonator with a Q of 300,000. We can see a T1 of 1/3 of a second, much shorter than we were expecting, given that the T1 should be minutes to hours. Then we can do the same experiment with a Q of with the other resonator that has a Q of 100,000. You can see that on the same piece of silicon just next door, we can measure a relaxation time of a second, which is indeed 3 times longer as expected. So that's already a very good indication that this is not a spontaneous emission from the spins. It's enhanced by the cavity. I'm done. Okay, 1 minute. Okay. So the final smoking gun is to detune the cavity from the spins because this Purcell effect is the numbers I gave you were for being right on resonance when the cavity and the spins are right on resonance, but of course the effect falls off as you move the cavity off resonance from the spins. So you might expect the relaxation time to follow this kind of behavior where it reaches a minimum right on resonance with the cavity and then goes off. Of course, it doesn't go off to infinity. There'll be some intrinsic relaxation time. And so we expect to measure some kind of plot that looks like this in terms of relaxation as a function of detuning. So we can do that experiment. And OK, I use the same colors just to convince you. It looks just as one would expect. T1 far from the when the spins in the cavity are off resonance. It goes out to thousands of seconds. But bringing the cavity and the spins onto resonance causes the relaxation time to fall by 3 orders of magnitude down to the region of a few seconds. So this is really engineering spin relaxation using the Purcell effect as Purcell predicted about 70 years ago. Okay, so in summary, I've tried to tell you that bismuth donors are really a fun system to work in. They have a very rich Hilbert space thanks to the nuclear spin and the strong coupling. We can use clock transitions to protect the spin from magnetic field noise, extending the T2 to 3 seconds. And there's some interesting changes in how the nuclear spin bath around the donor varies as you move to the clock transition. And finally, because of its large zero field splitting, bismuth donors are nice systems to study with superconducting resonators and other circuits. And we've used that to show cavity-induced spin relaxation. So here are all the people that have contributed to the work I've discussed. I'd like to especially acknowledge the group from Saclay and Jared for the Purcell work. Gary Wolfowitz is in here, and Gary, whose name is obviously in black, for the work on clock transitions. This is the photo of the group, and thanks for your attention.
Thanks for a nice talk. I was just wondering what kind of control you have on the placement of the dopants in silicon. Like how do you place them? How can you choose freely how close together they are?
Yes, so in this work, I guess the critical parameters would be how close they are to the surface, because that determines how closely they're coupled to the resonator, and that we can tune using the implantation energy. For the work with superconducting resonators, these bismuth dopants were implanted, and then you can choose the dose that will give you the concentration of dopants, and you can choose an implantation energy. So at that level, that's quite tunable. At the level of controlling the position of individual dopants, that gets hard if you really want to use through space interactions. If you wanted to build, say, a spin chain of dopants, perhaps that's where we're going with it. We've tended to try to avoid coupling schemes that rely on that because it's difficult, and there are various ways to create multi-cubic gates that don't require precision. But there is a technique based on STM that allows you to place phosphorus atoms with very high precision on a surface. It's based on taking hydrogen-terminated silicon. You use an STM tip to remove some of the hydrogen, and you crack in a bit of phosphine gas, and the phosphine attaches to where you've dissolved the hydrogen. So it's still under development, but it shows that you can, within the precision of 2 lattice sites, choose where the phosphorus atoms.
But you don't have an equivalent for this for the heavier dopants?
We don't. No, we don't for bismuth. Yeah.
Thanks.
How easy is it to get into the polariton on the Rabi oscillation measure? Is that routine and straightforward, but just not interesting for you? Or?
No. So getting is in terms of the cavity work. Yeah. So for an ensemble of spins, it's not hard. You can always. So it's something I didn't say. If you have an ensemble of spins that are in phase, you have this root n enhancement of the coupling, which means you can always cram in more spins and get into the strong coupling limit. Then you have problems of finite coherence time and inhomogeneous broadening. So we tried to. So there's a bit of still a way to go to both get into that strong coupling limit and still have highly coherent spins. And that's something that we're working on by reproducing the work I've discussed, but at a clock transition for bismuth, where the lines get narrow. What gets hard is when you want to do that for a single spin. So for a single spin, we reckon that the coupling that we can get would be, at best in the sort of a few kilohertz. The gamma, the dephasing effective line width for a single spin, we reckon can be much less than that. So the spin is not the problem, but the cavity is the problem, because then you need cavities of well over 1 million if you're working at sort of gigahertz regime to get well below that. So I think the sort of the strong coupling where G is bigger than kappa and gamma will be hard for a single spin, but this high cooperativity limit, on the other hand, it should be well achievable for single spin. So the goal is to use that to be able to emit photons that are correlated with the spin state.
Hi. I was just wondering, could you go back to the bit about the bismuth transitions, please? You did a nice plot of data that you took. There were some peaks.
Okay. New computer, I don't know. That's probably was on. This one?
A little bit further back.
Further back.
Sorry.
Okay. Now show navigator. Okay.
It was a data plot rather than results.
Oh, this?
Oh no, sorry, further forward.
What transitions?
So you plotted the.
Yes, the one with the awkward split line shapes.
That's exactly what I was about to ask about.
Okay.
You said at the time that you could explain a little bit more about that. Sorry.
That's right. Yes. basically, what we're seeing here is an effect of the strain in the silicon on the bismuth donors. So aluminium and silicon have different thermal expansion coefficients. So when you have, if you think about, these are spins sitting underneath the inductor, which is just a wire of aluminium, and we're seeing the spins that are more or less underneath the wire within the silicon. And because of the compression in the aluminium, we have the spins directly underneath the wire are in silicon, which is under compressive strain, and the ones outside the wire are under tensile strain. So the center of where we expect the bismuth transition frequencies around here, and so basically one of these peaks is coming from the compressive strain, one of them is coming from the tensile strain caused by the thermal expansion coefficients.
Thank you very much.
So I was wondering if you can reach a density or can see effects where the bismuth atoms are so close together that you get exchange interactions?
Yes. Yes. So that's been seen for various donors. The signature of that is that you get the signature of the first of all the effective hyperfine coupling starts to fall because the electron spin is sampling different donor nuclear spins, and so it views some kind of average, and you begin to see for the strongly coupled dopants, you see a transition frequency right in the middle of the spectrum, which has effectively zero hyperfine coupling. We don't. So far, all experiments have been done on. It's all randomly doped, so you have a range of exchange couplings, and you try to pick out different regimes based on the transition frequency. But eventually, in the future, one could try to engineer regular arrays with stronger couplings.
That's it.